and then I want to select a specific model, access BAC's product selection. Log in.
Joe's stingy with the information, not giving us the information.
Stingy? What you talking about? I'm showing to you right now. Anyway, so once you get inside the BAC product selection page, you just have to register for it. They'll give you an account. You can select pretty much any of the units they have to offer. From cooling towers all the way down through ice thermal storage. What we tend to use a lot is we use the adiabatic condenser selection. Don't let it fool you. It says condenser, but it is for a gas cooler for CO2.
Okay.
You select your gas, 744 in this situation.
Okay.
Let me go back to my schedule. I'll look at my conditions and I'll select a real world adiabatic gas cooler for this system. Okay. All right, so you always take the THR off the medium temp side of life. Do not consider the low temp because the low temp is dumping into the medium temp.
Mm-hmm.
So when you get your THR, it's always off the medium temp. We got 52.27. 52.7. Okay, and then we just gotta pick our city and our state. We know that we're in New Jersey. And it was Millville Municipal. All right, and then we know that we don't care about the elevation because we know it's pretty flat out here. We can pick our gas cooler temp. We know that on this specific design, we were at 87.3. So 87.3. Suction superheat, make that 12.
Wait. What is that? That's
suction temperature. Sorry, suction temperature. You always want to use your lowest temperature. So that would be your minus 20 here. Okay, so minus 20.
Okay, all right.
Superheat, set that to 12, just for the gas cooler selection. Gas temperature in 139 degrees.
Wait, is that assuming that you have 12 degrees of discharge superheat?
No. That's the superheat on the low temp side of things. The maximum superheat you're going to see possibly. For the gas.
On the suck. Oh. Suction. I'm still confused. You're talking about the suction line superheat of the medium temp compressors?
Yes.
Because that's on the medium temp, they're typically supposed to be a low of 18.
Total superheat, right?
Oh, okay.
Total superheat. We're talking about usable superheat out of the evaporator.
Oh, never mind.
That's what they want.
Okay, never mind. Sorry.
Yep. And then did we have a custom pressure here? I know we did.
For the flash?
Yeah, let me look at my
536.
Let me look at my well, I got to look at my compressor printouts. Just bear with me. I got to see what I put in here. 580 for the intermediate pressure. 41.
Oh.
Nope, that was a previous selection. Let me open up the one that we actually finally decided on. I believe it's this one. Yeah, there we go. Okay, high pressure. Well, that's the intermediate pressure. I'm looking at. Okay, so the high pressure was set to auto here, so we just let it ride here. If we're selecting this, you can select your compressors for a higher high side pressure than what you're actually condensing at. If you're trying to look at a transcritical side of life. In this case, we know that we selected it for auto, so it's going to select it for whatever temperature your condensing is.
Okay.
Keep it at that.
So you don't have to worry about that. Okay.
This changes based upon whatever you put in for your gas cooler outlet temp.
Gosh.
I only want one unit. I'm going to say two because it might not be able to do one with theirs. And I'll go -5 to 50. Perfect. I'll just hit select models. You can pick it based on price ranking or estimated energy use.
Let it ride.
I'll do it on price ranking because our customers are very concerned about first cost.
Yeah, I get it.
Yeah.
Who is it?
So you hit the button and you just wait for it to pop up.
Oh, if it comes up with some dumb error, I'm going to lose it.
It's not going to, I don't think. I hope not. It's going to tell me that it can't find one.
Enhance. There we go. See, that was the magic one right there. I just did it.
All right. So once you get your selections here, you can see here with the BAC model, it tells you here what the connected horsepower is in this back number.
Gotcha.
This tells you what the total heat of rejection of the unit is, what the capacity of the unit is. This tells you what the reserve capability is. In this situation, I would select this 30% here.
Does that tell you how many fans are on there by that model number or no?
It tells you with the TSDC2. Yeah, it tells you right here. See, it says 3.1 horsepower fan motors.
That's a big bastard. So the 2 of them, huh?
2 of them, yeah. Yeah. If I want with this one, that's a 14 fan, but that's 47% over. So I don't need that much. I'm only looking at 20 to 30% on my gas cooler, so that we can overcome those hotter ambient temperatures.
So here's another thing I wanted to ask you, Joe. Why does nobody integrate split into these gas coolers?
Great question. So we've experienced this with clients where they've actually requested us. We're specifying Trillium condensers on regular BX designs, and they asked us to split. And we've actually gone back to BAC, and they said that the maldistribution from having one coil side running and one side dead could adversely impact the system.
How so?
Because the system is expecting airflow coming in from 2 sides.
Uh-huh.
And the fans will pull harder when it's pulling in from one side because that other coil is dead and there's no heat.
Oh, because the coil is going to expand just a little bit, which is going to cause a little bit more restriction than what it would, right?
Correct.
I mean, it's minuscule, but it's still enough to affect the airflow.
Yeah, but I mean, if you ever look inside these Trilliums, sorry, Kevin. If you ever look inside these Trilliums, you're going to see that the fin spacing is very minimal on those coils.
Mm-hmm.
Yeah.
So that seems to be like an issue at like almost every single CO2 store up here. Is we have tons of gas cooler for the summer, or a decent amount of gas cooler for the summer, but then winter hits and we are just
you're oversized.
Yeah.
Yeah. And even when you're running static, no fans, you're still oversized?
Oh yeah, big time.
Really?
The wind,
and then it's just the load at night. We don't have a lot of load at night because I mean the majority, probably a lot of that load is your flash gas load. So all the VFD compressors, most of these manufacturers are sizing everything off of that peak flash tank load. Well, that VFD compressor may be the only one running in the middle of the night, and it can't keep up.
Sure.
It's just short cycling.
Even the VFD is causing short cycling?
Yeah.
That compressor's running by itself?
Yep.
Wow, that's pretty amazing. I mean, are we talking a supermarket here, or are we talking a cold chain distribution warehouse?
Supermarket,
really? Open cases or closed?
Open, but they bring nightshades down at night.
So they're essentially closed at night. Yeah, and that's when all the issues happen, especially in a 0-degree day. Yeah.
Yep, that's when the load drops off, and then it wants to shut off, and then all the CO2 wants to sit in the gas cooler. It doesn't want to start back up. But like if they were able to split that condenser, I mean, it would probably put a little bit more load in that flash tank, and it would probably help out tremendously. But it seems like nobody, we're using standard gas coolers, no adiabatic, like just standard like Guttner gas coolers. Yep. We're still not splitting.
Wow, really?
No.
In that case, if it was a traditional type, air cooled, slab coil with fans on top, and you could probably header that for 50% split. But I don't think CO2 is still pretty early in its inception in the United States, and I think a lot of manufacturers are still just worrying about those hot summer months, making sure the system is sized correctly for the worst case condition.
100%.
I mean, if you look at DX systems, the same exact thing happened a long, long time ago. They were worried about, let's size our system for the worst case scenario. And then nobody started worrying about the low end conditions until many years later, right?
Well,
go ahead.
No, one of the things that Kevin and I were talking about, like if you could put an offset, or not an offset, but basically change your subcooling set point on your like your 326, your iPro. So like typically most of these ones are set for like 5 degrees of subcooling off there, right?
Yep.
Where if you would turn it down to 3 degrees, right? Yeah, you're getting less subcooling, fine. But that's going to open up your HPV more, right? Which is going to put more pressure on your flash tank, which inadvertently would put more load on your medium temp. So you're robbing Peter to pay Paul, but I'd rather have, the compressors have a solid load than just, not as being as energy efficient as what they could, because they're already falling on their face because of the load, right?
You're almost talking about like hot gas injection, basically, like false loading, right?
Essentially.
Yeah.
The problem with hot gas injection is you're really robbing Peter to pay Paul, so you're not actually doing anything. I mean, it is, it isn't, but like increasing that flash tank load, that's you're pushing Peter down the stairs.
No kidding.
That was amazing.
It works though, like it works like a charm. It loads that rack up, and everything just starts purring.
No, pushing Peter down the stairs.
It's just like hot gas bypass in an HVAC system, right? It's the same idea. You're just keeping some load on the system to keep it running.
Gotta get that zero zone hot gas bypass valve. Thing's just like throwing a hot dog down a hallway. That thing is just like wide open.
It's good. You want to try to maintain those compressors, keep that load up.
It'll add that superheat right back to them, so you don't got to worry about liquid flood back on that.
Right,
well, and this dovetails nicely into what I'm about to go into, which is the line sizing for CO2 systems.
Okay.
So this is a recant of the last session that you had with me. I brought up the same exact tool that we had open last time. You'll see here now that this tool does offer CO2 and ammonia.
Oh no shit.
As well as some other fancy refrigerants that we use. What we do is we basically just set up, we mimic our legend in here, put in our loads, evap, suction temp, room temp. If we have any valve pressure drop, we can put it in here. It automatically ports over to the line size table.
Mm-hmm.
And then we come over here, our line sizing, and you can see here we've already done this, but I mean, look at the mass flow of the system. 24,000 pounds per hour, 25,000 pounds per hour.
Damn.
So that will tell you right there why our line sizes on the mains are so large. Even though, coming down here, this is one thing to note. This tool's also been set up for stainless steel, not copper. So you'll see all inch sizes here, not eighth sizes.
Gotcha.
But you can see like a 4-inch line on a 2,500 MBH load. You're a 4-inch line. Call it a 4 1/8 line. You're looking at 1,800 feet of velocity and a pressure drop of 0.29 pounds. Like, so that's normal.
Go back over. I want to see the total, because that's for the whole loop, right? The how many pounds per hour?
24,774.4
pounds of refrigerant per hour.
Correct.
How many pounds are in the said system? Estimated. I mean,
I think it was like 1,200.
That's it.
Yeah, but it's flow in the system. Like it's high. It's a high flow system.
Crap.
Yeah,
that seems really low.
Right.
Yeah.
I mean, the Target I just started up had 1,000 pounds on it.
Are they doing any heat recovery on any of these?
No.
Why?
Because they have no need for it. It's a freezer. It's a freezer distribution warehouse.
Oh, okay. So it's not like a process.
There's no need for hot water. There's no AC. There's no nothing. It's a big building that's a walk-in box, basically.
All right, never mind.
With some offices in the front. I
got you. So it wouldn't even make sense to do a little heat reclaim core. This would be stupid. Never mind. Dumb.
Yeah, no, you would never get the benefit of putting it in. The ROI would be way, way out there, probably 7 to 10 years. You know what I mean?
Nah, who cares at that point?
Yeah, who cares? Once you're done installing it, who cares, right? But I mean, if you look down, so our main branch is pretty large, but you look that we maintain a very constant velocity throughout the whole loop, right?
Yeah.
We don't let it vary down very far. We want that CO2 to push out to the system, and we want that oil to entrain and stay with the refrigerant to come back to the system.
Okay.
Keep our velocities up. We keep our pressure drop low. You can see here that it tells you at the end of each circuit. This tool is intelligent enough to tell you what the saturated suction temp required will be for that circuit.
Okay.
And if you look up here, you see your rack saturated suction temp is minus 22. You're well within your window of what the compressors are operating at.
Well, hold on. No, even go lower. There's one that's negative 21.1. So like you don't have
higher than negative 22.
So how the hell are you doing that with pressure drop? Because that's a lot of pipe.
It's a lot of pipe, but with CO2 you get like 7 pounds to every degree of pressure drop.
Damn it, that's right.
Yeah.
Okay.
You get a lot of pressure drop in CO2 because it's not a mixed refrigerant.
Yeah, all right. Never mind.
Yeah. And then on our liquid lines, we got to carry a whole bunch of liquid out. So, we try to keep our velocities on 150. Causes us to have to go with the 3-inch line from the main, but then we immediately split once we get in the building, go to 2.5 and 1.5. Or 2.5 and 1.25. Sorry. Yeah. And then for all the coils, we either go with 1 inch or 3/4 based, 3/4 connections based upon the coil connection size or whatever is required there.
Gotcha.
So, and then we go over to the medium temp side of things, and you can see here that your pressures are obviously higher, right? You're going from 200 pounds to 500 pounds because you're medium temp now, not low temp. And our max flow requirement over here is 5,600 pounds per hour.
Why does it say 2 loop 5s? Like why does it say AM1, AM1, AM2, AM2?
Oh, so okay, so you see that this says parent up here?
Yes.
This is the parent loop that this segment name feeds off of. So you got AM5 here.
Oh, okay.
These two feed off of AM5.
Okay, now I understand.
And then AM3 feeds off of AM4. So AM4 has AM3 and loop AM5 off of it.
Understood. Okay. All right. That cleared that up.
That's the way our tool works. So now one thing I want to bring up when it comes to line sizing for CO2, especially in supermarkets, you're going to have situations where you're going to have a 2-door case on the end of the lineup. You're not going to be able to get the velocities that you want. You just have to go 3/8-inch piping and live with it, whatever it is. Like, for example, risers especially. You got a pithy little 4 MBH load. That's nothing on a CO2 system. You're gonna end up with velocities on the riser of like 600 feet per minute. It is what it is. You just got to live with it. Hopefully, all the mass from the rest of the system will kind of pull that gas up the riser and help it to get that oil back to the system.
It is such a nightmare when they're throwing up 3/8 pipe and it has 1.5-inch armo on it and supporting it in the ceiling and not making it look like complete dog shit.
because it tends to bend and belly really bad, right?
Oh yeah, it's like a bunch of bananas.
Yeah. Yeah. Well, one thing that we put into our plans when we do CO2 designs, we actually have an interval support detail that we put in just for CO2. And for all the given sizes, we have a maximum distance that you're allowed to run between your supports.
Oh, yeah. Usually it's like 6 feet, but like.
No, we go lower than that. We go 3 feet on 3/8.
Yeah, it's got to be like that or even less sometimes.
Yep.
It's terrible.
Yep. So yeah, and then once you this all dovetails into let me go over to our piping summary over here. Sorry, we were at 1,800 pounds. Sorry, I misspoke.
Yeah, that extra 47 you forgot about.
Yeah, sorry about that.
No. I just with how much mass flow you had, I'm thinking like there's got to be like 3,000 pounds in this thing.
No. So no, there's 1,800 pounds in the system, and then we look at we size the flash tank off of that. We know that we want to be roughly 40% oversized with the flash tank, so that we have room for the gas volume to push down on the liquid. Basically, we don't want to size that flash tank for 100% full.
So my question is, do you size for how much refrigerant you have out in the line size, and let's just say you're going to maintain a 20% flash tank level.
Yep.
Okay, so you assume whatever that level is plus plus that's how high, so you don't get all the way up to 100% because you typically cut off at 80, and so you don't
We
kill your
take
compressors.
real simply, we take our refrigerant charge out in the field piping, take 25% of that, and then we multiply that by 60% so that we're not filling the receiver basically, or
Gotcha.
filling the flash tank. And then that's what we tell the OEM, and they help us size it basically.
All right. So one more time, you take the amount of case piping volume of refrigerant, right?
Yep. That volume of CO2. Yep.
Okay, and
then you multiply that number by 25, 1/4. Multiply it by 1/4 because we're not using the flash tank as a full pump down device.
Okay.
Okay. We're only using it as an operational piece of equipment when the system is running. We're not looking at that. We may be able to pump one circuit down into it, but not the whole store.
Okay.
So we take 25% of our total refrigerant amount,
and
then we multiply that by 60 to get us, and then we figure out what the flash tank needs to be at that 60% level, and then that's where we get our size from. And one thing you'll never see in a CO2 system, you'll probably never see horizontal receivers again, or for horizontal flash tanks. They're all vertical because what they're trying to do is they're trying to maintain a solid column of liquid out to the fixtures and surface area, right? If the receiver or flash tank's standing up, you've got a smaller surface area to push on than you would with a horizontal.
It's funny because Zero Zone is installing lay down receivers in all their target racks.
Are they really?
Yeah. We just started up another one this week.
Wow.
I mean, I'd say that'd be okay for like Cascade or what.
I'm not gonna lie,
it increases your charge, doesn't it?
A little bit, but
Yeah.
it seems to be a lot more user friendly. The rack isn't as tall, and I kind of like it. Because they're able to use a mechanical level gauge.
Okay. Like a Rochester gauge or whatever. Yeah.
Yeah. So no more just on-off switches. It's actually got a mechanical level gauge.
Yeah. Are those level gauges pretty good with the CO2?
Seems to be, yeah.
Huh. How about that? That's news to me. Seriously.
Wow.
They're the only manufacturer I've seen do it, though.
Right. Yeah, you're not going to get a rack out of Hill Phoenix that's going to have anything but vertical flash tanks. Number one, because that's when they bought Advancer, that was their prototype design. And why change a good thing if it's working already? You know what I mean? So
if it ain't broke, don't fix it.
That's right.
You got no gas in
it. So let's see. What else can I show you guys about sizing of CO2 systems? We typically use the Danfoss Cool Selector software for valve selections when we're doing AKVs or CCMT valves. That's a pretty simple, straightforward process. For anybody out there watching this podcast, if I mention a software, please go out and download it, give it a try, because if I use them every day, then it's really worth it. Seriously. And like the PT chart that I brought up before, no, it's proprietary software for our company, so you can't have it. Sorry, don't ask.
Oh man, when we did the piping one, there was so many people that were like, "Can I get that software?" It was like kind of like that.
You know how many people reached out to me about that, and I was like, "Nope, sorry, I developed that software. You can't have it. You can't offer me enough money to have that software because it's my sword and shield." You know what I mean?
Yeah. It was almost like the Dave Chappelle show with that guy. I gotta give me some of that pipe size and diagram. Give me that.
So yeah, I mean that's basically that's the gist of sizing a CO2 system. When it comes to sizing heat reclaim coils, things of that nature.
Yeah.
Really we rely on the vendor to do that. We'll reach out to the evap coil vendor. Typically we use Ref Plus or somebody of that nature that has a CO2 coil already.
Oh, so you'll rely on the customer to basically tell you, okay, this is how much heat I want to actually kind of see if I can get away with taking away from this rack, and then They'll give it to you, or you'll do
No,
it?
no. So we as the engineer figure out how much heat we can get out of the CO2 system. Then we tell the evap coil manufacturer or the heat reclaim coil manufacturer how much heat we have to offer. And then they give us a coil selection based upon that heat.
Okay, so now I have a question then. So typically, how cost effective is it to just either A, run off of the normal rack as it is, versus actually putting an offset in the controller to have another heat reclaim set point to keep your pressure higher to get more temperature out? Is it fairly cost effective because the compression ratio for CO2 is shit, so the energy consumption is already low? Am I wrong?
So it's better than DX, that's for sure. And you know,
Okay.
this line of questioning and thinking has been an issue for a very long time. A lot of people have actually fought over the fact of, hey, I can use heat reclaim, but I have to keep my head pressure up if I do that. Which one makes more sense? Do I keep my head pressure up and do heat reclaim, or do I lower my head pressure and not do heat reclaim and take the benefit from that?
Because it's still electric energy that you're basically utilizing to do that, right? And the only reason
Correct.
why I said, if anyone's ever figured out the compression ratio, it's very low. It's like 3-to-1 on the one set of compressors and like 2-to-1 for the other. It's when I explain transcritical booster systems to people, it's usually upper level mechanics that I'm talking to, and I'm like,
Yep.
it's comparable to having like a compound Carlisle compound compressor, right? Because you're
Pretty much.
basically taking the low temp and going through 2 cylinders, getting it up to that intermediate pressure, which is usually 68, 78 pounds, then goes in the ass end of the Carlisle, and then comes out at whatever your ambient and your head pressure ends up being.
See,
Yep.
I'm a fan of just using whatever heat we have and not forcing them into TC mode and just using whatever heat we have, because it's usually still a decent amount.
It
even
is.
even at like 70 degrees, it's still a decent amount of heat. So why raise the KW any higher than you need to when you could get whatever you can get out of it?
I agree. I agree with you 100%, Kevin. Seriously.
But it depends on what you're trying to do, right? So if they only had electric heat for, let's just say they have industrial water heaters, right?
Yep.
And you could basically do that without having the material of the actual electric driven water heaters, right? You can just do that through heat exchange and whatever else, right?
You'd be surprised what you actually get out of it still, even not being
You
TC.
would.
It's a lot.
Okay.
Yeah. The quality of heat coming out of a CO2 system is like really, really substantially better than a DX system.
Gotcha.
Which
It's
is
like
why, which it really comes back to, why do we have to worry about hot ambient climates, right? Or hot ambient climates when it comes to CO2? It's because the heat generated off of that system is so wonderful.
That's what I didn't understand, because like most people, they should make the investment, especially down south, make the investment of actually utilizing heat reclaim, because it's just another form of high ambient strategy, right? It's just another way to get rid of more heat away that you're throwing away anyway. Most stores, that they need some sort of dehumidification. When you have dehumidification, you need some sort of constant heat load. Well, shit. If we're running transcritical in the middle of San Antonio, Texas, just roll it. You know what I mean? And use that ROI.
Sure. But I mean, the thing that people are fighting over now is, when it comes to heat reclaim, you get a lot of pumped systems off. You get a heat exchanger at the CO2 rack, and then they pump glycol from there into the coil, into a glycol coil that's in the in the mechanical unit.
Mm-hmm.
Because a lot of the mechanical, a lot of the people that or sort of say, a lot of the mechanical equipment companies, HVAC system companies, are not actually comfortable putting a CO2 coil in their unit.
Really?
Because they're worried about getting CO2 out of the space, not putting it into it if there's a leak in the coil.
Okay, I get you.
Hey, talking out the other side of the mouth. You know what I mean?
That was really Jersey right there. Extremely Jersey.
Hey,
just wrap the other side. I got this stuff. It out of the back of the truck. Phil just fell.
I live in Pennsylvania. I don't live in New Jersey.
Yeah, right.
And I've been all over the world, so.
Did you? Can't now. Did you also? Were you the ones that designed the controls as well?
Yes, we did. Yes,
Okay.
these are our plans. As you can see, this is our logo right over here.
Okay.
We put this riser together. Kind of showed what all the boards are that are connected to the system.
Mm-hmm.
The leak detectors that are all connected to the system. how they're connected, what kind of wiring, the CC550s, how they're connected, what order they're connected in. And then we have, IO points over here kind of listing this is more for the manufacturer than anything else so that they can put together their board populations when they build the rack, basically.
And the service guy.
And the service guy, yeah, so that if they don't label the points on the boards, you can go to this drawing and say, oh, that's where that is.
Exactly.
Yeah.
Forget about us.
Thrown out.
Yeah.
What's that, Kevin?
It gets thrown out every time.
No, it doesn't.
But
sure does when it ends up in a binder or a book instead of like labeled to the rack.
So one thing that we do in our specifications is we call for a PVC tube to be installed if we're doing a machine room, and the plans go in there. Laminated plans go in there. If not, if it's like a rack house or something like that, we want the plans laminated and posted on the wall. It's in our specifications. I wonder if you guys have ever walked into any of our installations. Seriously.
No, I haven't.
I have.
Well, you have?
Yeah, the place down in with the valves. Hot gas valves. It was an old ammonia system, and then we converted it to 449.
You're catching me cold. I'm sorry.
Nah, you're fine. This is a couple years ago.
Okay.
Distech was the EMS system they were using.
Okay. Yeah, that sounds somewhat familiar now. Yeah.
Yeah, we'll talk about it later. It's fine.
Yeah. No.
Man.
Yeah, so here we show all the case controller. We show all the comm wiring, case controller locations, and then all the sensors. Things of that nature. Horn and strobe, leak detection sensor.
Is there a certain strobe that you have to do for the leak detection, like showing that that's a high concentration of CO2?
Yeah. So okay, this is what I found out from Dan Foss. When it comes to CO2 and leak detection, unless you have a drastic leak, the leak detectors are not going to pick up on a leak. It's got to be like a dump because you got people that are walking through these spaces, they're breathing out CO2 all the time. So there's some insensitivity to CO2 inherently in the detectors.
Yeah, because normal spaces have about 400 parts per million to 600 parts per million. A classroom will have like 800. Right? Yeah. I'm sorry, Kevin. I cut you off. I'm sorry.
Yeah, they're extremely unreliable with that. Like it's got to be just absolutely blowing for it to go.
It's got to be a dump. Yeah.
Damn.
But I mean, we've got all these jurisdictions that don't know what CO2 is, and their inspectors are all very, let's say, hesitant about these new system installs. So we have to show leak detection in our documentation, whether it works or it doesn't, because it makes them more comfortable and able to sleep at night, right?
Well, like when I did a store up in New York, up in upstate, and there's for even regular HFC or HFO refrigerants, they had to have a shut off via the leak detector that would enable, basically signal to the BMS or EMS that shuts down the circuit. They would basically shut down the EPR, shut down liquid line solenoid with the hopes that it would stop leaking, right?
Sure. Yeah, you're isolating the coil basically, right?
Correct.
Yeah. And that's what we have here. You'll see we have a liquid line solenoid, even though we have an EEV. That allows us to positively shut down the system, basically.
Okay, so I have a question about that now because I had asked this question we just went to the NASRC out in Cali, and they were talking about EPRs in the system, and they were like, well, you're always going to put a check valve in parallel. But then I thought about it. If you're using an EPR for temperature control, right?
Yep.
It's going to make that pressure higher than the out, so it's going to start bypassing on the check. So what he said after he told me that in the training, I'm like, that doesn't make any sense because I'm thinking about it. If you're just using as a suction stop, it would probably be fine. But you can't use it. Go ahead. Sorry.
So the only time that we put bypass check valves around devices in our CO2 refrigeration systems is when they can positively shut, basically, like a solenoid valve, like a hand valve, like that, that kind of stuff.
But EPR will close.
Yeah, Brett. So the way they have to do that, because I just had to do this at the store. You have to check it to the liquid line. So
Oh,
you have to check that EPR. The inlet to the EPR has to check back to the liquid line. So that way, if it ever gets higher, it'll check back into the liquid line, then check back to the receiver.
oh, I understand now.
Got it. Yeah, you can see here from our detail sheet, we only show piping installation, bypass check valves for anything that isolates. These are specifically for isolation ball valves.
Do you guys trust the internal check valves that they have out there?
We do, and we allow the contractors to use them if they so choose. That we don't have a problem with that. We know that they're way more expensive than a check valve and a isolation ball valve.
But the labor. But now
Yes.
you have to have a cat that's gonna weld all that.
Well, here's one thing that we do. We get the OEM to furnish all these valve branches to the field.
Oh,
So you just sweat one time, sweat another time, you're done.
Yeah, they always come all field built.
Yep.
Got it.
Yep. Yeah, and that's why we put the detail in our drawings. That allows the OEM to build them to what we need, basically.
Damn. All right.
Yep.
I'm learned in some stuff.
Another important thing to worry about with CO2 systems, you got to get that relief. You got to get that relief piping out of the area where you're serving, where the rack is. This is way more critical than a DX system because the high side pressures are so much higher.
Can you zoom out for a second, because I saw something I was going to ask you about, and then a little bit stop right there. Heat exchangers. So you guys are number 7.
Number 7. Yeah. Yep.
So, I don't know. Even on HFO and HFC systems, it kind of scares me, like with the being able to, go back in. Or what kind of heat exchangers are they using on this? What are they speccing?
They typically use the HX series from. Oh my God, who's the manufacturer? I'm trying to remember.
I know who you're talking about. I can't remember.
Yeah, it's like the HX 100, 150, so on and so forth.
Is that stainless or is that?
They make them in stainless now. Yeah.
Get the hell out. All right. Yep. Well, that I would trust then.
Hey, you got to, in order to stay competitive in industry, you got to adapt, right?
Yeah.
And they adapted, so yeah.
That's the one that has like the gray shiny tag with the blue letters on it. Yeah.
Correct.
I just can't remember the name of it. I can remember what it looks like.
And neither can I. And then, just some piping techniques for how to pipe CO2 systems, because they are a little bit different than DX systems.
Okay, so why? So I've heard this from other people, and I want to hear your approach on it.
Yep.
Why is the liquid line, supply line, branched off of the side rather than the bottom?
Good question.
I know. I want to hear what you say.
So the reason they're tapping off the side is because they don't want maldistribution of the liquid. They don't want it to all travel to the path of least resistance.
Mm-hmm.
So if you tap it off the side, you're going to get even flow on both sides. You're not going to get starving on either side of that bushing.
Okay. All right, that makes sense. Well, so that being said, could you basically, you remember the situation where you said where you had like 2 8-foot cases that are together, and then you had like a 2-door end cap with shitty flow? Could you essentially bush down at one point, because like you said, the pressure drop in CO2 isn't like dramatically bad for like the temperature change?
Sure.
So in that instance, couldn't you basically put a bush down maybe the 2 other cases to get a little bit more even velocity through?
You could, but you run the risk of not serving those other 2 fixtures properly.
Shit. All right, never mind.
Again, robbing from Peter to pay Paul.
Hey, Paul,
right? Yeah.
Or as Kevin would say, kick Paul down the stairs.
That's what refrigeration really all comes down to. I mean, everything deserves what it deserves, and that's the only way it's going to work.
Kicking Paul?
No. No. You get a fixture, you got to give it what it's asking for, or it's not going to work, right?
Yeah, gotcha.
Yeah.
All right, and I see. Well, risers. I want to go to risers. The traps. I'm sorry, the horizontal traps at the top. Okay, yeah. So they still do a conventional trap.
Yep.
Okay.
Yeah, we want an inverted P at the top, and we want a standard P trap at the bottom.
Okay, so anytime you have a transition, you have to have the inverted trap, right?
Yes, and the inverted trap is always the size of the riser. The standard trap's always the size of the horizontal before you hit the riser.
Okay, and then go down a little bit again, because there was more piping stuff I wanted to ask you. Keep going. Right there. Okay, double riser. So
Yep.
would you have? So let me ask you on these Guteners. I know sometimes they could potentially have two different sets of coils in there. Any of them like that, where you'd have a different capacity, or would you even need a double riser? Because I mean, your velocity is staying the same all the time. It's a processing place, right? I mean, it's storage, right?
So typically when we have two circuit coils, like you're talking about,
Mm-hmm.
we do them a lot for another one of our clients. What we do is we provide two EEV valves,
Mm-hmm.
and we pipe them individually from the drop, basically.
So you act like two separate coils.
Circuits. Yes.
Okay,
yes, we treat it like two separate coils, so that you don't have to worry about doing a double riser.
Two liquid lines down, two suction lines going up.
Correct. That way, if one shuts off, that pipe goes empty, and the other one continues to run.
So why would we use this double riser situation that we see here?
So the double riser is great for situations such as in a supermarket where you have a long lineup of cases in the middle of the sales floor. You bring one loop over, it's all medium temp. You bring one loop over, you drop down one feed to keep the false columns small as possible. And then you loop off at the bottom of it to feed all the fixtures. So let's say you're serving 8 fixtures on one loop, on one drop. If you don't have a double riser there and 4 of those cases shut off on satisfaction, your mass flow will cut to half, and your riser won't be sized properly to get that oil back up.
Because you typically need the X amount of velocity to get that oil return, correct?
Correct. And the neat thing about a double riser is just the way it operates, basically. So you got your pipe sized here for the full mass flow of the system. The trap here is sized for the full mass flow of the system. What happens is when you go to part load on this side of life, you're going to get half the mass flow here. It's going to fill this trap with oil because the oil is going to become unentrained in the refrigerant.
It's going to become a restriction, essentially.
Yep, exactly. It'll fill the trap. It'll cause a restriction, and then all the gas will be formed up the smaller riser, increasing the velocity of the flow.
I've never heard it explained that way, and I get why, but like no one's ever actually sat down and explained it that way. That was actually a really good explained, Joe.
That's how a double riser works. That's why we do it.
Okay.
And I can't tell you how many contractors I've had call me and tell me, why are you speccing double risers? I don't get it. And I have to explain it to them every time why we put them in and how they work. You know what I mean?
I got why they worked. You know what I mean? Because you're wanting that, but I just didn't think, okay, it's actually filling up with X amount of oil. Once it fills up with oil, then it blocks it, causes the restriction, which causes the refrigerant to go up. I just never thought it through that way.
Sure. And most contractors won't. No fault to you guys because you're in there to install the equipment, get it up and running, right?
No, I'm going to throw this back at you for coveting information. That's why you don't share anything, and that's why technicians don't know.
You just got to get closer to me, man. I'll share everything I got with you.
I think I need a 20. I'll gladly pay you. I'll pay you Tuesday for a hamburger today. All right. So are you guys are doing jacketing and everything on this, right?
Yes, we are. We ran all the piping on the roof of the building.
Oh, okay.
And we're just popping in for each evaporator. So we double insulate it and jacketed it.
It's gonna cost more than the welding.
Probably is, but I mean the labor's cheaper because you can get anybody to do insulating, right?
Yeah. Well, I mean, I didn't realize Kevin was the one that brought it up to me. He's like, "Yeah, Armaflex is just about as much as piping at this point."
We're on this job. We are not using Armaflex. We're not using elastomeric. We're using polyisocyanates.
English? What?
Sorry, I'll show you the note. Here's the note. This is what we're using. We're using the polyiso from Johns Mansville.
It's basically styrofoam, Brett.
Basically, it comes in 2 pieces and
you couldn't have just said that. You were like, you had to call it like whatever the chemical name was. Break it down to the electron.
Because that's what I deal in every day, dude.
God, freaking engineers. That's why no one likes you.
Yeah, that's true.
That's what I said. That's why no one likes you. Styrofoam. Just call it styrofoam. Yeah, hard rigid plastic or hard rigid foam that gets pushed together. Until my TV comes in. Man, I think my head hurts. Kev, you got any more questions for Joe? Fuck.
Yeah, I'm wiped.
This is our just last detail on our detail sheet. This is our hot gas evaporator detail. Kind of shows how the piping goes for a hot gas, CO2 evaporator. We got our electron expansion valve up here. Gas goes through the coil, life is good. We got our defrost relief regulator here set for 55 degree CO2 refrigerant. Because
so it's holding back. It's holding back, trying to keep 55 degrees saturated, which will keep the temperature up.
In the evaporator, right?
Yes.
So this is an essential item when you're doing hot gas defrost.
This is exactly like any a lot of industrial systems I've seen, where they usually have that Hansen regulating valve where it has 2 different solenoids on it.
Yep.
One for positive closing, one opening up 2 at the same time or something like that for regulation, and then the other one's for fully open option.
Correct. Yeah, wide open feature. Yeah. Yep. So that's basically where we're at. The hot gas, when you go into defrost, hot gas comes up this line. Hot gas, solenoid opens. Gas passes through the drain pan first, and then goes up through. There's a check valve here to prevent backflow. Goes up through the coil and then back through the suction line.
So, service tip on this, guys: if you're dealing with this type of system where it's going through the pan first, a lot of times in industrial type situations, you can leave the unit in hot gas for a little bit. When you're doing that, find the drain and plug it, because a lot of times what will happen is that hot gas pass will melt all the ice, then the water will drain out, and now you're heating nothing, because you're basically heating up the air insulation that's in between the coil and the ice. And so that way, at least if you keep the water in there, it can transfer the heat from the coil up to the addition to the ice that's still there.
That's a good point. That's a really good point.
We used to do it a lot, because guys would call and they were like, "Oh, we got 2 evaporators that are iced up." I'm like, "There's 60 in there. I'll see you Monday." And then we basically go up there. We'd wrap them with like a tarp around the back, around the front, plug up the drain, let it sit for 2 days. Hey, brother, I'll see you in 2 days. We'll come back, and by then everything's all de-iced, and then unplug the drain, away you roll.
Sure. Wow, that's a great suggestion. Seriously. So,
thanks, Joe.
Hey, no problem.
I appreciate you coming on. Kevin's. What time did you get up this morning, man?
1:30.
Oh my gosh.
Yeah, one beat, and I still got to go clean up the entire garage.
Was that for work or for personal stuff?
For work.
Oh my goodness.
Yeah, that's all week.
Get out of Chicago.
Yeah. Changes all week. We're doing them by the airport, so we were sneaking the fucking crane in before they realized we got to crane up. We're probably gonna get a fat ass ticket.
Nice. All right. Well, Joe, thanks for.
I appreciate it. Yeah, I learned a shit ton. It's always a good time having you on.
Hey, I appreciate it. And guys, if there's anything else I can do, please feel free to reach out. Let me know. I'm here to offer whatever I can from my years of experience.
All you have to do is just Google Joe's name and you'll get his phone number. Apparently.
Don't tell anybody that.
All right, guys. We'll see you next time.